The next talk will be by Aleksandr Pinzul, and he's going to tell us about exact results in noncommutative AdS2 CFT1 duality.
Hi, it's nice to participate in one more about anniversaries. I'm pretty sure that we will participate in many more. So, unfortunately, I could not come. So because I'm in the middle of the semester. So, but I'm glad to give a talk anyway. So the talk will be essentially like not repetition, but I mean exactly on the same topic as the talk which I gave recently in Corfu. So several people, of course, will see that this is essentially the same talk. But I still decided to give this talk because I mean, like non-commutativity and BAL, they have very long history, and especially in my case, that was the main topic which I collaborated with BAL until recently. I mean, so just recently, we somewhat started working in a different direction. And also, there is a positive thing that if the internet connection drops, you can just go to YouTube and listen the Corfu talk. So in any case, so though the title is some exact results, so exact results will come only like at the end because they're more or less technical. So the main point of the talk will be kind of motivation why to do this stuff. In addition to the standard motivation because this is fun and all stuff. So this is more or less the plan of the talk. As I said, we'll just discuss more or less the geometry of the AdS space in the Lorentzian signature, Euclidean signature. What is the specifics of two-dimensional case? And then we'll pass to commutativity and, as I said, some exact results. So mostly this project was initiated with Alan Stern 2-3 years ago, something like that. But Fidelia participated at some stage, and of course, I mean, there were contributions from our students. So the AdS, DS, and spheres, of course, I mean, they're very intimately related. So here's some standard things about the isometries, right? So just looking already isometries of different spaces, you can see that okay, so there should be some relations already on the level of the representations and all that stuff. And so, but in two-dimensional case, this relation actually is much deeper, which has its consequences. So meaning that specifying d equals to 2, you see that the various groups, they actually are the same groups. So meaning the isometry, for example, of the Lorentzian AdS2 and Euclidean AdS2, they're the same, and actually de Sitter also the same. What is different, actually, of course, cosmological constant and some reshuffling of the signature of the embedding space. So the main difference between Euclidean AdS and Lorentzian AdS is actually in the topology, not in the isometry. So as usual, when you consider Lorentzian signature, then you will have some closed time-like curves. So meaning that you will have some hyperboloid, rotational hyperboloid, where rotation will be exactly as shown in the picture. So that's why whenever you consider Lorentzian AdS, you actually don't consider that embedding per se, but you consider universal covering, right? You just decomplexify the time direction. And that's why actually you have all those patches when you color already this decomplexified AdS2 in this particular case. So this Poincaré patch, and you have all this possibility of the physical consequences depending on your choice of the coordinates, actually. So we will see that in the Euclidean case, the situation is somewhat different, but still we care about Euclidean case because our primary interest actually to do kind of, if you wish, like non-perturbative check of AdS CFT conjecture. So, but of course, I mean, first I would like to give some standard arguments. Why do we care about non-commutativity in this particular setting? Because there are many reasons why to care, starting with just pure mathematical ones. I mean, so, but because, as I said, our goal is to check AdS CFT correspondence, our take on the non-commutativity exactly as some non-perturbative quasi-classical effects of quantum gravity. So there are very well-known arguments why quantum gravitational effects should lead to some non-classical space-time. And arguments given by Fredenhagen, Doppler, Roberts, they're quite universal, meaning that they essentially are model independent. And of course, I mean, this audience knows very well those arguments. And they show that independently of what the theory of quantum gravity will turn out to be, actually, it should be some kind of non-commutativity. At least there should be a regime where the space-time appears as a non-commutative one. Then there is a general belief, I mean, I would say it's maybe not that general, but I mean, you would like to believe, I would like to believe that the symmetries, they're quite rigid things. So I mean, that they survive for quite large scales. So meaning that even if the quantum gravitational effects will kick in, we still would like to have some models which respect the symmetries before the quantum gravity actually started to play some role. So maybe in some the symmetries will be somewhat modified. I mean, so but still it would be nice to have some non-commutative models of space-time which respect the regional symmetries. So classical example of that would be, of course, a fuzzy sphere, which is the most studied probably model for the non-commutative space, and Ball has made very important contributions to this model. So essentially, you can think of AdS2 as some non-compact analog of a sphere. So that of course tells us that the whole business will be mostly about the representations. Okay, so so this is the argument. I mean, so I will not repeat it. I mean, due to Doppler, Fredenhagen, Roberts, that quantum gravitational effects should lead to some space-time uncertainty relations, and the non-commutative algebra is the realization of those relations. Okay, so the fuzzy Euclidean AdS2, as I said, I mean, is a natural generalization of a sphere, of a fuzzy sphere. So that's why, of course, I mean, it's also it's been introduced already some time ago. So the idea is, as I said, exactly to have some non-commutative generalization such that still respects that SO21 or SU11 isometry in some sense. So that isometry should be implemented on the non-commutative algebra. So that is nicely done if you know that this AdS, Euclidean AdS, or actually not necessarily Euclidean, Lorentzian AdS2, has a natural Poisson structure with Killing vectors given by the Hamiltonian fields essentially associated with that Poisson structure. Okay, so and then if you have this structure, of course, I mean, then you know how to go ahead and quantize at least formally. So to do actual calculations, of course, you would like to have some kind of local coordinate. By actual calculations, I mean that to put some field theory and extract some corrections and all that stuff. I mean, typically it would be nice actually to have some analog of local coordinates. So many people, including Nassim, so we did that for fuzzy sphere, for example. So here, for fuzzy sphere, in some sense, it's more complicated because it's a finite-dimensional matrix model. So here, it will turn out infinite-dimensional because it's a non-compact. So in some sense, it will be easier to do in this non-compact case. So, but in the commutative case, as I said, there are many different coordinates, and depending on the situation, one or another set of coordinates would be preferable. So the standard ones, this Pfefferman-Graham set of coordinates, which leads essentially to what you call typically to Poincare patch. Right? I mean, so here is the metric. So, but the Poisson structure, Poisson brackets, not very much trivial, so they're quadratic. So it's not immediately at least obvious how to quantize in terms of these coordinates naturally. There are so-called global coordinates, also very natural ones, which have very nice property of having the canonical Poisson structure. So meaning that at least formal quantization in terms of these local coordinates, and because you remember, as we will see, this is some non-compact space. So formally, you just quantize in terms of these coordinates as a model plane. So what is very important, so in some sense, you can take this as a hint of some of AdS CFT correspondence, that these Killing vectors in these coordinates or in these coordinates, so these coordinates are much nicer to see. I mean, so the conformal boundary here in this Pfefferman-Graham coordinates corresponds to z going to +0. And then, at least naively, you can see that the Killing vectors on the boundary, they do generate the one-dimensional conformal transformations. Okay, just usual translations, dilatations, and superconformal transformations. So this is another, this is the main reason why these ZT coordinates are quite convenient, because I mean, in terms of x to y coordinates, the conformal boundary corresponds to x and y going to infinity, and typically you want to bring your boundary to some finite distance, so you can actually analyze it much better from the point of view of just what are natural boundary conditions. Though of course it's equivalent. So as I said, quantization, of course, as usual, it's about representations. So SO21 or SU11 is a non-compact case. So clearly there are no finite dimensional unitary representations. And there are 4 families of infinite dimensional unitary representations. Those families are well known since 60s, no, probably 70s. So you would think that each representation should correspond to some physical situation. And as we will see quickly, in some sense, this is the case. So only one these representations will correspond to the case of our interest. So those representations are classified by Cartan, of course. I mean, so Cartan clearly is just essentially physically the radius of AdS or ds, the radius of your embedding. So here's the Cartan alpha. Here we keep just as a deformation parameter to keep track of non-commutative effects. So epsilon, some another parameter. M is discrete, so it's really the spectrum of some variables will be discrete. Of what variable we will see later on. So anyway, so those are 4 series, and the identification could be done like more or less like that. I mean, so just looking at the Cartan, we see that for the principal series, the radius will be negative. So which corresponds, I mean, I wrote in Coast series, Lorentzian AdS2. Then there is supplemental series. Series, they also have a negative cosmological constant. But as you can see, the radius, so K controls the radius, as I said, radius cannot go to infinity, so it cannot be made classical. So it will be always a quantum case. So we call it quantum Lorentzian AdS2, meaning that quantum which does not have a classical limit. And then those remaining 2 series, discrete series, they correspond to this last free parameter, epsilon being fixed, correlated with K, with control, which controls the radius. They exactly correspond to the geometry, to the classical geometry of the Euclidean AdS2. So here is, as I promised, a striking difference between Euclidean embedding and Lorentzian embedding. So the Lorentzian embedding, you remember, was also hyperboloid, which you had to decompactify to get rid of those CTC. So the Euclidean case is also a hyperboloid, but which obtained by rotation around a different axis, and it's made of 2 disconnected parts. So it also has like 2 boundaries as a strip in the Lorentzian case, but those boundaries are disconnected. So those 2 series, this discrete series, they exactly correspond whether you want to work quantize like this half or this half. So that actually could be made very concrete when you look at the representation, because I mean these coordinate plays the natural role of radius, radial coordinate. And you can see that the representation of embedding coordinates will actually tell you whether you considering the embedding of the of this upper half of the AdS2 within AdS2 or lower half of AdS2. Just looking at the sign of the corresponding embedding coordinate global, not global, the embedding one, the three-dimensional space. So, but what is important that the radial coordinate gets really quantized. Okay, so this is the M is discrete. So in terms of the radial coordinate, the boundary, as I said, is at infinity. So that corresponds to this quantum number to be very large, point to infinity, strictly speaking. And it could be sent to infinity because it's infinite dimensional representation. So the representation could be established explicitly given really the representation of all the embedding coordinates, and as a consequence, you can read off from here the representation of x1 of the radial coordinate, just like from here. If you take the difference, then you see that it is a radial coordinate. Radial coordinate is given by multiplication in this space. So here is the. You remember that in the commutative case we had this the global coordinates and z and t. So the relation between z and r away from the boundary, z equals 1 over r. Okay, so because for r the r equals 0, this is the center of the AdS. So r goes to infinity. This is boundary. So 1 over r brings the boundary to plus 0. So, but as I mentioned, to quantize, it's much more convenient to use those global coordinates x and y. So here's somewhat quick and formal consideration, but you can at least pretend doing that much more rigorously. So of course you can easily go back and forth between x, y, and r and t. Quantize in terms of x and y, the small star, and then you can formally just go back using the classical change of variables, go back to r and t, or if you wish, z and t. So it's very surprising, at least to me, that the classical change of variable in the model star, so take this usual model star, the classical change of variables will lead to exact quantization of this Poisson bracket, means without any quantum corrections. So you formally just put t hat, z hat, z square hat, and the star which will realize this non-commutative algebra will be the model star just written in terms of the new variables, once again, without any quantum corrections. Because strictly speaking, you might have, you could, after quantization, you can have some quantum corrections, or non-commutative corrections. So, as I said, so okay, so that would be our non-commutative AdS2. Now we, of course, we would like to do something with that model, and as I said, our interest was to check AdS CFT in some sense beyond the classical gravity limit. Because as I said, for example, from the Fredenhagen and company argument, you can see that non-commutativity, if it's really the effect of quantum gravity, this is a non-perturbative effect. Okay, because the argument goes through the creation of black holes, and as we know, the black holes cannot be described. The creation of the black hole cannot be described by some perturbation theory. So, very quick review, like 1 page, 2 pages, what we would like to do without entering whether AdS CFT actually some valid and sound thing or not. So let us think that it makes sense, and we want just to check whether it makes sense beyond some approximation, or it's just like a really artifact of very high symmetry. So anyway, so we consider just scalar mode, the excitation of AdS by a scalar. So this is the more or less most general scalar field theory interacting on AdS, on two-dimensional AdS, equation of motion, conformal dimensions, essentially. And what you do with this, as usual, so we just will follow the standard prescription, which could be motivated, of course. So you calculate the classical solution for this theory, and calculate on shell action. Because of the presence of the conformal boundary, that will be non-trivial, meaning that it will reduce, in the classical case, to the evaluation of the action on the boundary. Hence, this correspondence between the theory, whatever it is, which lives on the boundary. So in the commutative case, the whole thing could be done nicely, again, due to the very high symmetry of the space-time background, meaning that you can really calculate, find three solutions exactly. For the interacting theory, you can find the first non-trivial corrections in terms of lambda in this interaction constant. You can plug it back. So this is the solution, of course. So the K being bulk to boundary propagator, G being bulk to bulk propagator, and plugging back. That's actually the main object which you typically have in this. Okay, so this is boundary, and in the case of the interaction, you have also some bulk contribution, of course. And the prescription, AdS CFT prescription, is that now your action will become the functional of the boundary conditions, essentially. So phi0 is the some field which lives on the boundary, which controls the behavior of the solution in the bulk. So essentially boundary condition. So you treat those as being sources for some actual observables on the boundary. So I mean that this is some partition function, generating function. If you believe in that, then you just do the usual thing, right? I mean, you vary with respect to your sources, and you obtain correlators. So if you do that in classical case, that would be your answer, clearly showing that the boundary theory for those observables, unspecified, it's a conformal one, right? So we would like to do this as much as possible in the non-commutative setting. So in terms of this either operators or star products. As usual, the action is really just copy paste of the commutative one, but you should be just carefully put in, if you will, like star products. I mean, of course, it's more than that, but I mean, for us it would be enough. So where is the information that this is a really a fuzzy non-commutative AdS2? Of course, in the kinetic term. Exactly like in the case of a fuzzy sphere. So if you just talk about the algebra of the fuzzy sphere, it will be just the full matrix algebra of n by n dimensions. So how do you know that this is really a sphere? In the kinetic term or in non-commutative Killing vectors, right? I mean, so the fact that the kinetic term has this form exactly is the one which tells us that we're working on commutative AdS2. So this is the geometry. Non-commutative term controls the geometry. So why do we want to believe that some kind of AdS CFT still should work? Because the strong form of AdS CFT is the following: that if you have some space which asymptotically looks like AdS, then the theory on the boundary, some theory on the boundary, will fully control the bulk theory, meaning that including even quantum gravitational effects. So how would, I mean, our space is fully non-commutative space. So how do we know like that it should work in any case? I mean, so what is this asymptotic of AdS, etc.? So the first hint comes from here. So as I said, I mean, so of course, I mean, now we can quantize easily isometry, because remember the isometry, the commutative one was given by the Poisson structure. So now non-commutative isometry preserving the algebra and deformed one, SU11, will be just given by the commutators of the embedding coordinates, essentially. Or you can rewrite that in terms of T in Z coordinates and star products. You will have the exact formula actually for the non-commutative killings. This delta being some notation, this is essentially non-local deformation of T derivative, essentially like sine of dt. But the point is that when you send Z to 0, so you understand that Z, because it's a star product, so it's like symbols of some actual operators. So when you send that to 0, then you see that these non-commutative killing vectors close to the boundary still produces the usual commutative conformal transformations. So in this sense, you can say that the boundary, that asymptotically, non-commutative AdS2 still looks more and more like the commutative AdS. The additional support to this fact comes from the following: that if you write this star product in terms of ZT, as I said, I mean, it's a small written in terms of ZT, and use the fields with the correct boundary conditions, I mean, so we know what are the boundary conditions, that the star product will actually go to the usual dot product when Z goes to 0. In some sense, it's very similar to the, not in some sense, it's exactly similar to the Moyle case, right? I mean, so we know that if you consider fields more and more regular, then the Moyle, by regular meaning that they don't change a lot at the quantum scale, then of course, I mean, Moyle product should become just usual product. That's how you recover the commutative algebra. So, but at the end of the day, and so like this is the argument why we should believe that we do have asymptotic AdS. So then, of course, I mean, let's start with the free case. So strangely enough, I mean, so when we started, we could treat even the free case only perturbatively. perturbatively in the non-commutative parameter, independently of all those things which I said, that let's preserve symmetry and all the stuff, and still we failed badly to produce the exact solution. And so that's why this talk, because I mean recently we managed actually to show that actually the free case, massless and massive, it does have very nice closed expressions for the solution for the scalar field and the fermionic field. So as I said, this part is rather technical, but in very non-intellectual way. I mean, so you really have to do a lot of calculations without involving a lot of some complicated math. So very helpful that the Laplacian could be written actually in this form. So that was in some sense what helped us to solve. I mean, it's a trivial transformation, but somehow we missed it. So if you do that, then doing kind of like separation of
Sasha,
variables.
You have 5 minutes left.
Yes. Yeah. Thanks. So doing the transformation, the separation of variable inspired by the commutative case, you can actually reduce this operator equation to the ordinary differential equation, just for the radial coordinate. And the point is that that is just usual Aleksandr equation, which you can solve once again, because I mean now it depends only on one operator, so it's just usual commutative variable. And so after that, we ran some non-trivial checks whether you can recover a commutative result, whether you can recover some our previous results, as I said. I mean, so we obtained only some perturbative in non-commutivity result. So those checks, I mean, just requires some special functions, some properties of special functions. So I will not elaborate on that. And so here's the massless case. So very quickly, so in some sense, you don't have to treat fermions, you don't have to find solutions for fermions independently, because we managed to show that the Dirac equation for fermions, which takes this form after some manipulations, has a solution if you know the solution for the, at least in the massless case, if you know the solution for the bosonic case, for the scalar field, then actually you can map it to the solution, to the fermionic solution. So you just take some two component spinor, and this matrix will map it to the solution of this equation. So those Greek letters, they're just combination of coordinates t and r. And just to conclude, so what will happen if you plug that into this prescription for the AdS CFT? As I said, boundary looks commutative, so you really only like bulk contributions will produce some corrections to the possible AdS CFT. So because for the free case we had exact solutions, so for the free case we could explicitly calculate the exact correlator, which we obtained exactly in the conformal form, and only prefactor got some corrections. For the interacting case, unfortunately, we still don't control completely, so we still have only some perturbative results, which support the conclusion that 3-point correlator still also has conformal form, only with the some prefactor modified. So to conclude, I just want to say that I think it's a nice topic. Once again, independently whether you believe in AdS CFT or not, because I mean it's a concrete calculation which allows you to do some non-perturbative tests of some ideas. I mean, so that shows actually the relevance of non-commutativity for these kind of calculations. It might give some ideas, better ideas, what is the dual side of this correspondence. Okay, so though it looks it should be like the simplest one, because it's, I mean, you cannot go like down and say AdS2 CFT1. Still, there is a lot of discussion what is actually the CFT1, because it cannot be just usual quantum mechanics and stuff. So this non-commutativity could give a very nice test to those considerations. So, and here exactly like what answers we already have by now, that we have some partial answer to exact results. Unfortunately, without interaction, we tested that for different for scalar field, for spinor field, and this is what we want to see. I mean, so mostly this last line. So because I mean, JT gravity recently has become of some very important it has become very important topic exactly in this relation. This AdS2 CFT1. So we trying to like revisit JT gravity also in this non-commutative setting and to see whether it will be helpful in clarifying some points. Okay, so I think that's what I wanted to say. So once again, thank you for your attention and parabéns, congratulations to Bao. Thank you very much.
Thank you, Sasha. Are there any questions?
Hi, Sasha. This is Kumar.
Oh, hi.
Hi. See, my question, at some point you said that you are assuming Brighton-Lohner-Friedman bound.
Uh-huh.
Now, we did the same analysis exactly for the same system, and we found that that particular bound picks up a correction from non-commutativity. Probably you know that calculation. So I'm wondering why you had to assume that it stays unchanged.
So here.
Yeah.
You're talking, I think it was your paper where you found some deformation, right, of CFT. Is that
right,
the
right. There was a deformation everywhere, both on the AdS side and the CFT side, and for the as a result on this bound, Brighton-Lohner-Friedman.
So in some sense, in this settings, so this is just commutative one. So, but when you do the calculation in the non-commutative setting, we did not assume that. So it came out more or less exactly the same delta came out in the non-commutative calculation. So let me see. Here in these calculations, the same thing came out. You see this new.
Right, we got a different new. Our new picked up a correction.
Right. So I think I should look more carefully. I think probably some starting points or some settings were different. So that's why in your model you do have corrections, and in this model we don't. So I remember that I was looking at, but now I forgot actually the details. But the point is that here we don't assume it. It's just if you violate, then of course I mean U becomes complex, and you just have completely different solutions, which will be having for us wrong boundary asymptotics and all this stuff. I mean, so here it just came as being result more or less the same way as in the classical case. But I have to look and try to pinpoint what exactly is different in our approaches. You know?
Okay, thank you.
Mm-hmm.
Hi, Sasha. So
hey.
the question is,
Hi,
you're mentioning Green's functions. But the star product and so on involve infinite number of derivatives. And it is not clear that there is a propagation of an initial data which defines a globally hyperbolic problem. Then I do not see why Green's functions should exist at all in these problems.
Mm-hmm.
Am I wrong?
Right. No, you're not wrong. In some sense, that was my starting point, our starting point, in thinking. Because, I mean, typically, as you know very well, I mean, so people doing some quite reckless stuff. I mean, so they say, okay, so let's put just star products and delta function and try to proceed and all stuff. But then the question is, what is delta function? Because, I mean, so if I just change the variables, the star product will change what delta function you use. Then people start putting some Gaussian regularization of delta function. So, but the point is that before going to star product, you can of course write, for example, equation, even interacting equation, just purely in terms of the operators. But then the problem should be just unique. I mean, so I just want to solve that operator equation. So when we say Green function, that's exactly in the operator sense. Like I have equation like fg equals to some other operator. So I want to invert that. I mean, so in this sense, I mean, so exactly like in the case of the fuzzy sphere, right? In the case of the fuzzy sphere, you can write Green function just expanding into spherical harmonics by truncating it. I mean, so, but the point is that because it will be given in terms of the operator, then it will be unique answer. You just, depending on what star product you use, you will have some expression. And because we're looking at the Euclidean case, of course, I mean, so I know that you don't like that, but in Euclidean case, it's not a hyperbolic problem, right? I mean, so it's elliptic problem. So, but it will be still, of course, very highly non-trivial, non-local expression if you pass to symbols. So that would be my answer. But because we don't know the answer, I cannot say more and whether we will succeed or not. I mean.
It seems to me that, okay, I may be wrong. But it seems to me that there is no real propagation equation because you will start getting pseudo differential operators. And then I have no idea what there is no propagation equation, there is no Green's function. That I know.
Right.
Okay. So I don't know how to interpret your answer because there is.
Right.
So, okay.
Once again, you're right, but because the calculation, once again, this is a formal calculation, but because it's done in Euclidean case, we want to have a kind of bulk to boundary, but Euclidean one. So once again, so I cannot make more statements because, as I said, I'm far from controlling this question. So, but question is very important, and your question is exactly what started me thinking about that. Okay, thanks.
Okay, so are there any questions from Zoom? Okay, since there are no other questions, let us thank Sasha again.
Thank you.